Hello class, we are back. So we ended up with shapes of molecules, geometry of molecules. And remember we said molecules are three-dimensional. But how can we represent these three-dimensional shapes in a two-dimensional surface like a paper? So that's what we want to do here. Representing three-dimensional shapes on a two-dimensional surface, for example, a paper. One of the problems with drawing molecules is trying to show their dimensionality. By convention, the central atom is put on the plane of the paper. Then the other atoms in the plane indicated as a straight line. To represent an atom which is in front of you, in front of the plane, we use a solid wedge. And the atoms which are behind you, what we have to use is a hash edge. So let's examine an example. Let's apply this to some molecules. Okay. So let's assume that this is a linear molecule. A, B, C are on the plane of the paper. Linear. Trigonal planar too. These three X and A, the central atom, are all on the plane of the paper. So these two A, these two X are also on the plane of the paper. This is bent. But let's look at tetrahedra. For tetrahedra, we have A and these two X. I'll put them. This is 1. This is 2. This is 3. This is 4. Based on this representation, to represent a tetrahedral structure, A, 1, and 2 are on the plane of the paper. This X, this wedge, solid wedge, is supposed to be the particle or the atom that is facing you. And this hash wedge, hedge, is that which is behind. So let's take, for example, these three are on the plane of paper. This one should be looking at you, facing you, pointing to you directly in front of you. And this one is pointing at the back. Let's look at trigonal pyramidal. This is pointing you, is facing you. This one is on the plane of the paper, and this one is pointing at the back. So just look at this. This one, you see, is facing you, this one at the back, and this one is on the plane of the paper. A and X are on the plane of the paper. Let's look at trigonal pyramidal. This 1, 2, 3, and A, which is in the center, are on the plane of the paper. Then we are saying that this one is looking at the back, and this one is facing you in the front. Look at it. This is the one facing you. This is the one with a solid wedge, and this one is with a broken wedge. All these ones are on the plane of the paper. Then look at seesaw. Seesaw, this 1, 2 are on the plane of the paper. This one shows that it's at the back, and this one is facing you in the front. So you see an example. Then octahedra. These two are facing you. This 1 and 2 and A on the plane of the paper. Then this one is looking behind. So see, these ones are behind. These ones are looking in front. Then this one is in the plane of the paper. Square planar. All of these are on the plane of the paper. Nothing behind, nothing in front. All of them are sitting flat on the paper. So let's look at some examples. So this is SF6, you see. So this is its shape. This is its shape. This is octahedral. So this is how you represent it. See how you represent it. There are some molecules that have multiple central atoms. Let's examine those molecules. Multiple central atoms. Many molecules have large structures with many interior atoms, many central atoms. We can think of them as having multiple central atoms. When this occurs, we describe the shape around each central atom. So when this occurs, you look at different central atoms and look at the shape on those central atoms. For example, this is a central atom. Central atom 1. Look at the shape, it's tetrahedral. Then this is central atom 2. Look at the shape, 3. So this is trigonal planar. Then this is central atom 3. You see that? So this is bent. So we have 3 central atoms there. 1, 2, 3. Shape around C, tetrahedral. Shape around C1, we'll call it C1. This is C1 tetrahedral. Shape around C2, trigonal planar. Shape around oxygen, tetrahedral bent. So you can see it here. Tetrahedral. Oh, this one has only 2, 1 and 2. We have tetrahedral and bent. Let's try to examine some problems that we have with Lewis structures. Problems with Lewis theory. Lewis theory predicts trends in properties, but does not give good numerical predictions of the bond strength and the bond length. It cannot be used to get the actual angle of the molecule. Does not predict the correct magnetic behavior of molecules like oxygen, which is paramagnetic, but the Lewis structure predicts it as diamagnetic. So those are some problems. And because of these problems, another theory was devised in order to solve this problem from Lewis theory. So we are going to look at the next theory, the valence bond theory. Valence bond theory proposed to take care of the shortcomings of Lewis theory. That's why it was developed. So according to this theory, bonds between atoms would occur when orbitals on those atoms interact. So that is what valence bond theory is saying. That bonds between atoms will occur. They can only occur when orbitals on the atoms interact. Orbital interaction. As 2 atoms approach, they interact to form molecular orbitals. The molecular orbitals will be more stable than the separate atomic orbitals because they contain paired electrons shared by both atoms. So that is the valence bond theory. So let's look at how this is done in H2S. So orbital diagram for the H2S. This is the orbital diagram. This is sulfur. Its valence electrons are in 3s and 3p. And this is how they are arranged. You have these 2 which are paired and these which are unpaired. Then it's adding to hydrogen. Hydrogen has one s orbital. So we need an interaction between this hydrogen orbital and this sulfur. But it has to interact with these ones which are not paired, this and this, or this. So it interacts with that and forms a bond. So that's the bond which is formed. This is the molecular orbital. So this is a new bond which is formed, the HS bond. But see, there's still one unpaired electron here. So another hydrogen comes with one s orbital. Now it interacts with this p orbital and forms another bond. So this is valence bond theory. So you can see the molecule here. So these are the new bonds which are formed, bonds which are formed. These are these two orbitals in sulfur which did not interact. They are filled. So let's examine the main concept of valence bond theory. The valence electrons in an atom reside in the atomic orbital or hybrid orbitals. That's what the valence bond theory is saying. So the valence electrons in an atom, they are still residing in the atomic orbitals or the hybrid orbitals. Another concept by valence bond theory is that a chemical bond results when atomic orbitals interact. 3. The shape of the molecule is determined by the geometry of the interacting orbitals. So these are some concepts of valence bond theory. So we'll talk about hybridization. Hybridization is defined as the mixing of different types of orbitals to make new sets of degenerate orbitals. So you are mixing up orbitals to make new orbitals which have equal energy. We call them degenerate orbitals. Please, we are mixing the orbitals. Same type of atoms can have different hybridizations depending on the compound. So the same type of atom can mix S and P, can mix S and 2p, can mix S and 3p orbitals and form compounds. So let's examine carbon. The energy diagram for carbon when it is unhybridized it looks like this. You have 2 electrons in the 2s orbital and the 2p orbital, 1, 1, and 1 is empty. So if it wants to hybridize, it can use only one of these p orbitals. So this is sp hybridization. It takes one of these orbitals, it takes the empty one, mixes it with the 2s, and you form the 2sp hybridized orbital. These ones are not mixed. So in this case, what will happen is that when carbon bond, when it has the sp hybridization, that's sp hybridization, it mixes s and just one p, is going to form a compound which carbon will have triple bond, like here. We are going to look at that. But it can also mix 2 orbitals, two of these p orbitals with s. In that case, we have sp2. This 2 is because it is mixing with 2p and 2s. But the hybridized orbital is sp2. So it takes 2 of these orbitals, maybe these 2, and mixes it with s. when it does that, the result is that we have sp2 hybridized orbitals. One is unhybridized, so it's only left with one orbital here. So these three are degenerate, so it uses it to form bonds. Example, you see it here. So there will be one double bond. Then we can have sp3 hybridization. In this case, it mixes all these four orbitals. It mixes them and come up with new four orbitals which are the same. Then it uses it for bonding. That's when we have this kind of structure like methane. The bonds are the same. So this is just an example to explain hybridization. So sp3 hybridization. Atom with 4 electron groups around its central atom normally have the geometry which is tetrahedral and bond angle 109.5 between the hybrid orbitals. The orbitals are hybrid. As I've told you, it mixes all its 4 orbitals. Carbon mixes them. Then it produces new 4 orbitals which are the same. We call them hybrid orbitals. They have the same energy. Atom uses hybrid orbitals for all bonds and lone pairs. So in this case, this carbon, you see 1, 2, 3, 4. This is sp3 hybridization. For hydrogen, hydrogen has just S. Then look at this nitrogen. This nitrogen too has 1, 2, 3, 4. So it's sp3 hybridization. Because it has 4 electron groups around its central atom. So this is sp3 and this is sp3. So let's look at the energy diagram. So energy is increasing. Look at this arrow. Energy is increasing. This is unhybridized orbitals of carbon. You see 2 electrons in the s and 2p. And you see the 2p has higher energy than the 2s. Look at it. The 2p has energy higher energy than the 2p. But it now mixes it. We call it hybridization. It mixes all this and come up with new 4 orbitals with the same energy. These are hybrid orbitals. This is carbon. So let's see how it uses these hybrid orbitals for bonding. So unhybridized, so this area like this side. These are unhybridized orbitals for carbon and nitrogen. It mixes all this because you want to form sp3 and come up with hybridized orbital which they have the same energy. Nitrogen does the same. Nitrogen mixes all these 4, 1, 2, 3, 4 and come up with new hybrid orbitals. See, they are now the same energy, sp3. Then now it uses it to bond with carbon. Let's see how it does it. So bonding with valence bond theory. Bond takes place between atoms when their orbitals interact. Interact means overlap. In order to interact, either the orbitals must be aligned head-on. When they align head-on, they form what we call a sigma bond. Or the orbitals must align sideways to each other. When they do that, they form what we call a pi bond. So this is how the orbitals interact to form the bonds. So in this case, they are sideways, you see. They are standing sideways. You see, this is a p orbital, py orbital. This is py or px. And when they interact, this is a pi bond. Look at how a pi bond looks like. And look at the 2 electrons that they have. You see the 2 electrons here in the pi bond. But when they come head on, you see when they come head on, I want you to look at it, one electron, instead they come head on, they form what we call a sigma bond. Look at how the sigma bond looks like. And you see the pair of electrons are inside. So sigma bonds are stronger than pi bonds. Why? Try to think about it. Look at these structures and try to think, why are sigma bonds stronger than pi bonds? Think about it. That will help us. But let's continue. So orbital diagram with hybridization. We want to look at orbital diagrams with hybridization. Hybrid orbitals plus hybrid or unhybrid orbitals on another will form what we call a sigma bond. So let's say hybrid orbitals plus hybrid or non-hybridized orbitals of another atom form a sigma bond. Overlap between unhybridized p orbitals on bonded atoms result in pi bonds. So let's look at it again. So when you have a hybrid orbital and it combines or overlap with another hybrid orbital or overlap with a non-hybrid orbital, it will form a sigma bond. But when you have overlap of unhybridized p orbitals on bonded atom, it results to a pi bond. So let's examine this. So I want to see this CH3 and H2 orbital diagram. So you see, these are hybridized orbitals from carbon. All of them are the same. And these are hybridized orbitals from nitrogen. All the orbitals are hybridized. That's why all the bonds are sigma bonds. You see, this orbital from this hybridized orbital from carbon interact with an hybridized orbital from nitrogen, it forms a sigma bond. All these bonds, these orbitals are hybridized. It hybridized with one hydrogen, it forms a sigma bond. The hydrogen bonds are non-hybridized. Hydrogen cannot hybridize its orbital because it has just one, which contains electron. So you see, because they are all hybridized, they form sigma bonds. Then nitrogen too, all this is orbitals are hybridized, they form sigma bonds. Let's take another example where you have hybridized and unhybridized orbitals. So CH2N2 orbital diagram. This is carbon. Carbon has sp2 hybridized orbital. Then has one orbital which is not hybridized. Nitrogen too has sp2 orbitals which are hybridized. They have the same energy, but you have one which is not hybridized. So the ones which are not hybridized, they form pi bond. Then all the ones which are hybridized, they form sigma bonds. You see this double bond? It shows the sigma bond and the pi bond. See, one is sigma, one is pi, because you have one orbital which is not hybridized. Then let's look at sp. Atom with two electron groups, linear shape, 180 bond angle. Atom use hybridized orbital for sigma bond or lone pairs, and uses non-hybridized p orbital for pi bonds. So let's look at HCN. So you have, this is sp, this is sp. See, all these bonds, you have one which is a sigma and the other ones are pi, because these orbitals are unhybridized. So that's it. You see, this is a sigma, this is the pi, this is the pi, because if it interacted with the unhybridized orbitals for carbon and nitrogen. That's why we have the sp. So this is ethylene. Ethylene too has triple bond. You see, this is the sigma bond, which has the hybridized orbital, sp hybridized. But these ones, pi bond, they are the two unhybridized orbitals. So they just interact to form pi bonds. Of course, this is sigma, because it's sp. This is the other carbon, which is hybridized. Sp, you know, the s and 1p orbital are mixed to form a degenerate orbitals, two degenerate orbitals. One is used to bond with this other carbon, and this is used to bond with hydrogen. This is the Lewis structure of ethylene. Yeah, ethylene. Oh, this is not ethyne. So sp hybridized atoms, orbital diagram. So we want to look at it. These are the unhybridized orbitals of carbon, unhybridized. This is for carbon and this is for nitrogen. Then they mix, each of them take just one orbital and mix it. So that's it. These are the hybridized. These are unhybridized. These are the hybridized. These are the unhybridized. So these hybridized orbitals will form sigma bonds. Meanwhile, these ones will form pi bonds. Let's see. So you see, that's a sigma bond for the hybridized. This one is paired, so base hybridized. But these are the two pi bonds which form this pi and this pi. Of course, this is S, we form a sigma bond. Okay, so now let's look at other types of hybridization. sp3d. Atoms with 5 electrons group around it. We call it trigonal bipyramidal shape. They have trigonal bipyramidal shape, or scissor shape, or T-shape, or linear. Remember? Use empty d orbitals from the valence shell. D orbitals can be used to make pi bonds. So they use empty d orbitals and mix it with the s and the 3p. They come out with degenerate orbitals, which they use to form those bonds. So let's examine it. sp3d. So sp3, the atom. So these are the unhybridized atomic orbital. Look at them. 3s, 3p, 3d. This is for phosphorus. When it mixes all of them, you see, you have now 5 orbitals, which we call sp3d. So these are 5. 1 plus 3 plus 1, 5. These are the 5 orbitals. Let's go to sulfur. Sulfur too has s, 3s, 3p, 3d. It mixes all of them and form sp3 orbitals. Look at them. it mixes them. The non-hybridized d orbitals are not shown. They have not shown them. You know, there are 4 extra non-hybridized orbitals. They are not shown. So let's see how this is applied. So these are the non-hybridized orbitals. So this is for S, the non-hybridized orbitals. These are the hybridized orbitals. For oxygen, these are the hybridized orbitals. This is the p orbital, which is non-hybridized. So all the hybridized orbitals form the sigma bond. But the unhybridized orbitals combine to form a pi bond. That's why you have this double bond here. So that's why the shape is like this. We want to look at sp3d2. So atoms with 6 electron groups around it, octahedral shape, square pyramidal, square planar, use empty d orbitals from the valence shell to form hybrid orbitals. D orbitals can be used to make pi bonds. So this is an example. Let's look at how these orbitals make. These are the unhybridized orbitals for S, 3s, 3p, and 3d. So, you know, D has 5 orbitals, so it uses only 2. The unhybridized orbitals are not shown. We did not show them. There are 3 extra which are not hybridized. Then for iodine, 5s, 5p, and 3d uses the 2, 3d. When it mixes them, you see you have 6 orbitals. 6, which are hybridized. They have the same energy. So it can use them for bonding. So in this table, it's just a summary. Hybridized scheme from electron geometry. So 2 is sp2, 3 is s, 2 hybridized orbital is sp, 3 is sp2, 4 is sp3, and this is the shape of the molecules produced. 5 is sp3d, and 6 is sp3d square, 3d2. So let's try and predict the hybridization of some of H3BO3. Predict the hybridization of all the atoms in H3BO3. What we need to do, we want to draw the Lewis structure. So this is the Lewis structure. We want to predict the hybridization of all the atoms. This is, you see, we have 1, 2, 3, 4 here. Make sure you count it. 1, 2, 3, 4 electron groups. So what's the hybridization? Think about it. So for oxygen, what's the hybridization? This should be sp3. Because 1, 2, 3, 4 electron. Let's look at boron. 1, 2, 3. What's the hybridization? 3. sp2. This is 1, 2, 3, 4. This is sp3. Then look at this. 1, 2, 3, 4. This is sp3. Hydrogen don't have hybridization. They are not hybridized. Okay. So hydrogen can't hybridize. Boron 3 electron group sp2. Oxygen 4 electron group sp3. Let's take another example. Let's clean this one. Let's take another example. Predict the hybridization and bonding scheme for all the atoms in NCLO. Draw the Lewis structure. This is our Lewis structure. Then let's count. 1, 2, 3. This is sp2. 1, 2, 3. sp2. 1, 2, 3, 4. sp3. So nitrogen 3 electron groups, sp2. Oxygen 3 electron group, sp2. Chlorine 4 electron group, sp3. We'll try to examine some problems of valence bond theory. Problems with valence bond theory. There are still properties of molecules that it doesn't predict perfectly. For example, the magnetic behavior of oxygen. Valence bond theory could not predict it. In addition, valence bond theory presumes that the electrons are localized in orbitals on the atoms in the molecule. It doesn't account for delocalization. So these are some problems. In order to answer this problem, a new theory was developed, the molecular orbital theory. So we'll continue with molecular orbital theory. So we'll stop here for now.